In our last segment, we talked about energy storage and how they show up in today's built environment. Before we move on, let's talk a little bit about what's inside the battery units. So, what's in a battery? When we talk about batteries in the context of energy storage systems, their hierarchy is a cell, module, then unit. A battery cell is a single unit of measure, the building block of the system. There can be hundreds or even thousands of cells packaged into a single unit. The shape of the cells can be cylindrical, like the AA batteries we're used to using, or they can be flat pouches or larger, prismatic shaped. Multiple cells are grouped together to make a module, and multiple modules are assembled into a battery unit. The unit may also be referred to as a rack or a cabinet, depending on how it's packaged and who is selling it. At the unit level, there will also be a battery monitoring system which provides feedback on the system status. The units are the major building blocks of the energy storage system. A good physical analogy here is like a carton of eggs. Each egg is a cell, the carton is a module, and the display case at the grocery store, loaded with the cartons, is the unit. Of course, in the case of batteries, they're all interconnected and work together in a system. Now that we agree on the terminology, let's get deeper into the electrochemical reaction that produces energy in the battery cell. A battery makes energy through a chemical reaction that produces an electrical current. The battery has a few main parts: a cathode, or positive electrode, an anode, a negative electrode, separated by electrolyte. When a battery discharges or provides power, electrons flow from the negative to the positive electrodes. And when the battery is recharging, electricity is applied and the electrons go back to their starting positions and the battery can be used again. The specific recipe of metals to make the battery is called its battery chemistry. So, what types of battery chemistries might you encounter? The most common electrochemical ESS are lead acid, nickel cadmium, or lithium ion, although certainly the industry is evolving with new technologies to address the challenges that we're talking about today. The first is lead acid. Historically, most battery energy storage systems were lead acid and nickel cadmium. So, lead acid batteries are cheap, they're widely available, and simple to maintain. They have a larger footprint and are heavier than the newer technologies, but they are stable and have a long history record. They were the first generation of batteries to be used in ESS, so they have a significant portion of the market share, and they're readily available from a wide range of vendors. If you ever walked through a data center or a telecom facility that was designed before 2015 or so, and saw racks of what looked like car batteries, those were most likely lead acid. And even today, they're still used in some areas where AHJs will not accept lithium ion ESS installations, or where building owners don't want to accept the risk that comes along with other battery technologies. Lead acid is also the battery chemistry that's most likely in your car if you don't have an EV, and the kind you're most likely to find in any given fire alarm control unit, the fire pump engine, or an aspirating smoke detector. Tried and true, they're reliable standby. The main fire risk of lead acid batteries is that they off-gas a small amount of hydrogen during charging, which is quite flammable. If not properly ventilated, this can cause an explosion hazard. But given how long they've been around, we've gotten pretty good at sizing ventilation systems to make sure there are no explosive conditions. Fire events are rare, and thermal runaway events are not common and less hazardous if they do occur. In fact, some people joke that with lead acid it's more like thermal walk away slowly. Next is nickel cadmium. Less common today, but may be used in some industrial and emergency power systems. They've been around about as long as lead acid, and their advantage is that they are more resistant to overcharging and temperature extremes than lead acid, and they have good reliability and durability. They also have a longer lifespan than lead acid, up to 20 years as opposed to the typical 10 years for lead acids. However, they contain toxic materials which introduces another hazard during the manufacture process, disposal, or a fire event. So, typical applications for nickel cadmium batteries would be those where safety is critical, the environment may be extreme, and the maintenance protocols may not be top notch. Occupancies where you're likely to see them are transportation, power plants, airports, and hospitals. Thermal runaway is possible, but the fire risk is lower than with lithium ion. So, then we have lithium ion, which has dominated the ESS market as of late, mainly due to its high energy density, small footprint, and efficiency. They also have about a 20-year lifespan and have fast charge and discharge times. However, they are more sensitive to extreme temperatures and are more volatile. As we've discussed, they are subject to thermal runaway, which releases flammable gases and intense heat, and are subject to catastrophic failures. It's important to note that the term lithium-ion battery actually encompasses a few different battery chemistries, including lithium titanate and lithium iron phosphate. But as of the most recent editions of IBC and NFPA 1, there is still one classification for lithium ion. Since coming to the market in the 1990s, they have taken over and are the most widely used type of BESS. They are in everything from small portable electronics like phones and laptops to larger e-bikes, scooters, EVs, and boats to very large data centers and utility grid systems. Given their high energy density, they are smaller and lighter than other batteries and are scalable. In large scale applications, their positives are that they have longer lifespans than other technologies, are more reliable, weigh less, and take up less space for the amount of energy. Despite the risks that we'll talk about today, the train has left the station, and they are here to stay, especially given our moves toward renewable energy sources and the desire for utility grid stability and efficiency. And this is why we're here, because despite all of these positives, they have been the cause of some of the most high profile ESS fire incidents in the past decade. In addition to the three technologies we've discussed, there are other technologies that hold a small but not insignificant market share that may fill the gap between the traditional lead acid and nickel cadmium solutions and the somewhat volatile lithium-ion batteries. These include nickel zinc and nickel metal hydride, which are emerging technologies but offer some advantages to the other chemistries that we talked about so far. Now you should understand a bit more about what is inside the battery energy storage system. We've looked at the building blocks of what makes a battery system, main battery chemistries used in ESS, and how they differ in design and risk. Next, let's talk about what actually goes wrong when these systems fail. While each chemistry is different, the failure modes for lithium-ion are what drive most of the fire protection concerns today. Although they may end that way, these failures don't start with a big fireball. In fact, some of the earliest signs can be subtle or completely undetected without the right monitoring. In the next segment, we'll talk through what causes batteries, especially lithium-ion, to fail, what those failures cause, and why they present such a challenge for our traditional fire protection systems. I'm Jocelyn Sarantonio. This is MeyerFire University.
This has been a preview of MeyerFire University. Join the next generation of fire protection experts at www.meyerfireuniversity.com.